So today's talk is about a recent work that I have done about some problems in representation theory, but which seems to have a large relationship to some conventional number theory. So given the occasion, I think I will do more of the number theoretic background to the problem, and maybe towards the end I will say where I got interested in it. So so here is a rather basic question. In number theory. So given integers, positive integers, a comma b, solve the equation. Ax plus by equals n for n greater than or equal to 0. So usually it is okay to restrict the generality, so assume that a comma b is 1. They are coprime. So one can define this function n of n as cardinality of x comma y such that ax by equals n and x is greater than or equal to 0 and y is greater than or equal to 0. So there are so it is well known and easy to see that this set Nn is non-empty for large n because a and b are coprime. So since a comma b is 1, Nn is non-empty for large n. So there are two obvious questions that one would like to consider. Question 1. What's largest n such that Nn is 0? And the second question is what does Nn look like? Meaning to give a formula for Nn for all n. So in some sense it appears that question 2 is a more refined version of question 1, but to me it appears that one can have somehow some knowledge about question 2 without fully answering question 1. So for this particular question, so there is an explicit formula for Nn, and which goes as follows. So it is known that Nn is lies between integral part of n by ab and is equal to something and nab plus 1. So somehow the difficulty in the answer is only whether it is 1 or the next one, and the answer is that it is n plus a prime n plus b prime n upon ab minus 1, where a prime n is between 1 and b, and similarly b prime n is between 1 and a, and A prime n is congruent to minus n by A mod B, and B prime n congruent to B mod A. So since A and B are co-prime, one can invert A mod B. So this is a meaningful object. There is a smallest, there is a unique integer A prime which is congruent to this number mod B within the range 1 to B. So this is a precise formula. It tells you what is this number Nn. So this is the answer for question 2, and the answer for question 1, which of course if there is a precise formula, one might say it should be just obvious from the precise formula, but maybe it does take some small checking to do that the smallest, largest n such that Nn is equal to 0 is A minus 1 into B minus 1 minus 1, which is same thing as AB minus A minus B. So I will do an example just to be sure. I mean, theoretical mathematics, it's always good to check against examples. So an example, look at A comma B equals 5 comma 6, and then this Nn equals 0 for n equals 19, but is greater than 0 for greater than. So this is same thing as A minus 1 into B minus 1 minus 1, which is 20 minus 1. So till so 19 is the largest integer which cannot be written as xa plus yb, but 20 onwards it can be written. So this is of course a rather elementary exercise which anybody can do, but what seems a bit impressive to me that more generally one can ask the question, the same question for the Diophantine equation. Which is Nn is equal to cardinality of x1 xd such that summation ai xi is equal to n, and here xi are greater than equal to 0 and ai are greater than equal to 0, and so to say that GCD of A1 AD is equal to 1. Same question. And once again, one is asking what is the largest value of n, and for which Nn is 0. And then the second question, what is the exact shape of the answer? Yeah. So, I mean, to me, it seems like a rather basic question in number theory. So, in fact, question 1 has a name. So, question 1 was asked by Frobenius, and it goes under the name of the question or something of Frobenius, and he got some answer of that form, AB minus A minus B, but only an upper bound or something, beyond which everything is good. So asked by Frobenius, who gave some estimates on the largest n such that. But looking at MathSciNet and Google search, I get the feeling that this problem seems to be continues to be well pursued, and there is no definitive answer. So there seems no definitive answer. So this is for question 1, and for question 2, which is precise form of NN for d greater than equal to 3 seems not known. And somehow I did not find much literature on this problem. So I partly know about this problem because one of my friends from IIT Delhi, whom I thought I might meet here, Amitabh Tripathi, has written several papers on this problem. And he told me that he had a student working, whom I met, who was trying to work this out for d equals 3. So ax plus by plus cz equals n. And even for that, the students seem to be suggesting that it's a big mess and there is no good answer. So maybe sometimes the problems are not pursued because even in the small number of cases you may want to try it out, there is no good answer. And I think till something else comes up, one doesn't pursue the matter any further. All right, so somehow this is what it is. All right, so so this was part 1. So next what I am going to do, right. So maybe the form of the answer is already suggestive to some people, but I was certainly ignorant of what that suggests. So in both algebraic geometry and in number theory and in many parts of mathematics, we are used to thinking about polynomial functions. And somehow if one said that the NN is a polynomial function, that would be certainly a great start. And polynomial functions appear in many parts of mathematics, but there are variants to polynomial functions which are what seems to be relevant to this problem. And I am going to quickly describe these more general forms of polynomial functions. So my setting will be, we will have a certain subset f of z to the power n. Yeah. Maybe z to the power d. And one will be given a mapping f from this to either z or to c. Maybe z contained in c. And so then one says that f is a polynomial function on f. So f is at the moment just a subset of z to the power d, and the typical example of a subset of z to the power d which I have in mind is the set of positive integers. So a typical example of a subset is x1, xd is all greater than or equal to 0. So f is a polynomial function of on f if f restricted to if so f is a function on capital F if f is the restriction of a polynomial function on z to the power d, which is maybe contained in c to the power d. So this is one notion. Then I will use this notion called piecewise polynomial. So by piecewise polynomial function, so functions are defined on subsets of z to the power d, and by piecewise polynomial we will mean that f is written as union of fi, a finite union, such that f restricted to fi is a polynomial function. And then the third definition is piecewise and quasi polynomial. So f quasi polynomial if there exists a lattice lambda contained in z to the power d of finite index such that small f restricted to lambda plus L is a polynomial function. So where L is a coset of lambda in z to the power d. So piecewise polynomial, quasi polynomial. F is a function on a subset of z to the power d always. Right, yes. Yeah. So then one can also define piecewise quasi polynomial. To be one in which this one is a quasi polynomial, where f restricted to lambda plus L is a piecewise polynomial. Yeah. So I mean, this may sound a bit abstract or something, but maybe best to illustrate with an example. Integral part of n by 5 is a quasi polynomial. It is not a polynomial because the integral part starts values 1, 0, 0, 0, then 1, 1, 1, and then 2, 2, 2, so on. And what one will say is that there is a congruence mod 5. If you restrict it on that, then it is a polynomial. Yeah. So this is a quasi-polynomial A, and B, piecewise polynomial, an example to keep in mind. Piecewise polynomial would be that, let's say, n if n is positive, and let's say minus n if n is negative. So this function on integers is not a polynomial function, but it is piecewise polynomial. All right, so this is some definitions. So eventually what one is hoping is that the arithmetical functions that one is interested in will belong to this class of polynomials. Not quite polynomials, but piecewise quasi-polynomials. Okay, so the next notions that I want to bring to you are from what is called convex geometry. And these are like first notions one encounters. So there is a notion of rational convex polytope. So I will just write the words integral convex polytope. Rational polyhedral cone. And the other one is strictly rational convex cone. Strictly convex cone. So one is doing counting, so this was part of the title of my lecture, counting integer points, and somehow the counting that I have been doing, it is not clear. It is the counting which is referred here. So first I define rational convex cone. So this is convex. So these are all subsets of some vector space VR, and inside that there is VQ, and inside that there is VZ. Yeah. So there is an integral structure on the vector space, which means that you are just given a lattice inside the vector space. Yeah. And to say that it is a rational convex polytope is the convex hull of finite set of points in VQ, and this is same as points in VZ, and this is same as convex cone generated by some set S in VQ, and this is something where if V belongs to the set X, then minus V does not belong to X. All right, so once again, these are rather simple and perhaps well-known concepts, but anyway, I am a bit of a novice on this, and it is always good to keep a picture in mind. So, standard example of a convex polytope is just this. So, this is generated by these points 1, 2, 3, 4, 5, and 6. So, by saying it's the convex hull, that means that you join them and you take the line and then so on and you get everything. So, those 6 points determine this compact subset of R2 with boundaries which are straight lines, which are themselves polytopes. Yeah? And this is just as simple as that. And to construct a rational convex cone, it is just this. So you may have started with 2 vectors P and Q, and in rational convex cone, you are allowed to scale it out. So you scale out this line and take the convex region. So this is what it means to talk about convex cone, and that strictly convex cone means that there is no straight line which is contained inside the cone. Yeah? Okay, so very good. So the title of the talk was counting integer points on convex polytope, and also I think it said Ehrhart theorem. So this is the theorem that I am talking about. So theorem is that let P be a rational convex polytope in VR. Yeah, and what one is going to do is to do this counting function Fpn is equal to set of points x belonging to P n times P intersected with Vz. And the theorem is that this function of n, is a quasi-polynomial. So quasi-polynomial are those which are polynomial on congruence class edge. Yeah. This and there is another aspect of this which says that if P is actually integral convex polytope, then this is in fact a polynomial. Then Fp is a polynomial of degree equals the dimension of P of degree. So this is one of the basic theorems in this subject. No, all n. That's beautiful. All n. So indeed, I learned about this theorem only recently, and I could not believe. Of course, counting problems are very familiar objects in number theory, where one tries to count number of integral points in some domains or the other, but these are domains which are bounded by these rational boundaries, the polyhedral boundaries, and the point is that there is a precise formula. So this is a problem which I learned from Ramamurthy in those days, that counting integral points in circle of radius r is related to the Riemann hypothesis. But here there is a nice formula, and one can come up with the formula without too much effort in low dimensions. Okay, so what has it got to do with the problem that I began? So maybe I should just say as a corollary that number of points x1, xn such that summation ai xi is equal to n is a quasi-polynomial function. And the way one sees this as a consequence of this theorem proof is that observe that the set x1 xn, x1 xd, x1 xd such that summation ai xi equals n is equal to 1 is a convex set, is a convex polytope, convex rational polytope, in RD with the usual integral structure, and our problem is nothing but counting points in n times p. So this statement that I began with, one can get some kind of theoretical answers by some generalities. So it appears to me that I am fast approaching what I am supposed to be lecturing for. So maybe I will now go a little more quickly. So the question about n equals cardinality of x1 xd such that summation ai xi equals n can be generalized further. And the way it is to be considered is that suppose C is a rational strictly convex cone. Together with vectors v1, vd inside C. And now the question that one will ask is to question will be that one will now count n of v is equal to n1 nd such that summation ni vi is equal to B. So you are given certain vectors V1, Vd in a certain convex region, and you are looking at positive linear combination of these, Ni greater than or equal to 0, and this will hit vectors in the lattice generated by the Vi, and the question is what is this counting function, how does it vary? Yeah, so this is the question. So this is called partition function. So for my interest, what is relevant is that so there is something called constant partition function. So this is a function of this kind. So G is a Lie algebra, and T is a subalgebra of, let's say, diagonal matrices. And then there is notions of roots and weights, and in particular there is things called in particular there are positive roots. And the constant partition function is denoted by two variables p, lambda, mu. This counts number of n1, nd. So this is the number of positive roots such that summation ni alpha I equals mu. So this depends only on mu. So there are these positive roots, and any weight which is in the Q span of the roots, you are trying to write it as sum of these vectors. Yeah. So it's a very different occasion here. So I should maybe say what these vectors look like and what one is doing. So there are these Lie algebra associated to SL3, which is called A2, and the Lie algebra is written like this maybe, and these are two positive roots alpha and beta, and this is this cone in which alpha, beta, and alpha plus beta. So there are these three positive roots, and one wants to express anything in that region as combination of alpha, alpha plus beta, and beta. And question is, how does it grow? Yeah. So there are theoretical answers of the kind that I discussed, that these are piecewise quasi-polynomial. But somehow in a specific situation, it is of interest to not only give a theoretical answer, but to compute it as precisely as possible. And the theory may say that it is quasi-polynomial in the sense that you have to take a lattice of this shape and you have to take so many regions, but maybe in the specific examples things might be better than what the generalities may say. So, okay, so therefore finally, so there is a well-known question in Lie theory. Question in Lie theory is that to a compact Lie group G, there are these irreducible representations V lambda which are finite dimensional. So these are parameterized by some lattice points of this kind, and question that is of interest. Question is that these V lambdas, they decompose as direct sum of eigenspaces for the diagonal torus. Spaces for diagonal torus. And among the eigenspaces, there is the more distinguished eigenspace, the eigenspace on which torus operates trivially, called the zero-weight space. And the question that I have been interested in is what is the dimension, what's the dimension of zero-weight space as a function of lambda. So, you know, this lambda is a discrete variable ranging over lattice points in a vector space, and somehow the best answer one might ask, one might hope, is that as lambda varies, these dimensions are polynomial functions. But of course life is never so good. These are not polynomial functions in lambda, these are quasi piecewise polynomials, and this is part of some generalities, but then in some cases I have. So in fact this work is done with one of my brothers, Shravan Kumar, but that is more about geometric invariant theory, etc., which I have not come to. So there are I mean, the variation of the zero-weight space as a function of lambda is somewhat complicated. One can prove theoretical results, and then one can calculate in some cases, but what is somehow perplexing to me, that just like I said that this problem about ax plus by plus cz has no nice answer, even in rank 2 examples, there are the rank 2 groups called A2, B2 and G2. So for A2 and B2, I think they are reasonably nice answers, but for G2, I mean, there seems to be no answer available. So problems soon become quite complicated combinatorially. So I was planning to show some slides about these polynomials. So to show them, you have to define various regions on which it is one polynomial on this region, another polynomial on that region, and then what happens on the boundary, and what are the congruence conditions. So it's a bit elaborate, but I think given that I am already over time, I will stop here. Thank you.